As the extensive research and development carried out in the field of Borough, the smaller, lighter diesel engines capable of high operating speeds, which have been introduced in recent years, have firmly established themselves as highly efficient, economical and versatile power units. Today, the universal appeal of these engines is exemplified in the wide variety of uses to which they are put. To mention just a few applications, they are powering taxi cabs, private cars, trucks, and lorries, and the diversity of machines and appliances playing such an important role in agriculture. The story of the development of engines is itself a fascinating with one aspect, the all-important and vital fuel injection equipment, upon which the successful operation of any diesel depends. From the earliest experimental days, this essential equipment had been under constant review. There was the initial cost to be considered, and equally important, desirability of reductions in both size and weight of the injection pump, simplification of driving arrangements, and so on. With all these requirements in view, CAV Limited, as leading manufacturers of fuel injection equipment, put in hand a program of research in conjunction with the technical departments of Perkins of Peterborough. A completely fresh approach was made to injection pump design, and intensive development work and testing led finally to the adoption and introduction of the DPA distributor type fuel injection pump. This pump is now standard equipment on many of the engines manufactured and marketed by Perkins of Peterborough. In addition to the advantage the distributor type of pump has to offer in regard to cost, there are many technical features which considerably heighten its appeal. Apart from its inherent simplicity, the design lends itself to compactness. Here is a comparison of the size of the DPA pump with that of a conventional inline pump. Both are 6-cylinder models with mechanical governors designed for similar duties. And here is another version of the DPA pump, this one with a hydraulic governor, which is smaller and even more compact. The design of the DPA pump lends itself to the simplest and least expensive forms of drive. The rotating parts are light and the inertia forces small. The pump contains no ball or roller bearings, no gears or highly stressed springs. And as the casing is completely filled with fuel oil under moderate pressure, no separate lubrication is required. The pressure within the housing prevents the ingress of water or dirt. A radical departure from orthodox injection pump design is the employment of only one pumping element, irrespective of the number of engine cylinders. As is generally known, it's been standard practice for fuel injection pumps, and this is a typical example, to be provided with a separate pumping element for each cylinder. The element comprising a plunger and barrel with a suitable means of output control. In the DPA pump, the single pumping element supplies all the cylinders in turn with their charge of fuel, with a distributor connecting the pump delivery to the individual injectors. The method of distribution is in some ways similar to that employed to distribute the spark in the ignition system of a petrol engine. Of course, the diesel engine has no sparking plugs, but with the DPA pump, the fuel oil is distributed to each injector in turn from the single pumping element. Here are some of the principal parts of the DPA pump. This is the hydraulic head, with its central rotating member, the pumping and distributing rotor. The rotor and head are machined to extremely fine limits and form a mated assembly. At one end of the rotor is the pumping section, where two opposed plungers work in a transverse bore. The plungers are actuated by cam rollers, which, as the rotor revolves, come into contact with a stationary cam ring carried in the housing. There is a central bore through the rotor which leads from the pumping chamber and connects with inlet and delivery ports. Here, in a sectional diagram, is the end-on view of the internal cam ring, in this case with 4 lobes as used for a 4-cylinder engine. And here, the rotor carrying the twin opposed plungers and cam rollers. In this, the inlet position, the rollers are off the cam lobes, allowing the plungers to move outwards as fuel enters. As the rotor revolves, the plungers are forced inwards by the cams and the pumping action takes place. The fuel between the plungers being expelled under high pressure via the central passage and ports of the distributor. Not being spring-loaded, the plungers move outwards by fuel pressure alone. This transparent model shows how the distribution is carried out. Through the center of the rotor is the axial passage connecting the pumping space between the plungers with a series of ports drilled radially in the rotor. The single radial hole is the distributing port, which, as the rotor turns, aligns successively with a number of equally spaced outlet ports in the hydraulic head, from which the injectors are fed. There is an outlet port for each engine cylinder. Only one is shown in this model. A similar number of inlet ports are spaced round the rotor. These are lined successively with a single port in the head, the inlet or metering port. The function of metering will be dealt with later. This ghosted view shows the complete cycle of charging, pumping, and distribution. With the rotor in the inlet position, the rollers are off the cam lobes, and the metering port in the hydraulic head is in register with one of the charging ports of the rotor. The distributor or outlet port is well out of register with the discharge ports in the head. Fuel, under moderate pressure, flows in from a transfer pump, through the actual passage in the rotor, into the space between the plungers, forcing them apart. With the rotation of the rotor, the relative positions change. The inlet port is now closed, and the distributor port is in register with one of the fuel outlets. The cams force the plungers inwards, and the fuel is discharged under high pressure to the injectors. And so the cycle continues. In practice, fuel entering the pump flows first through the transfer pump, which raises the pressure to an intermediate level. The transfer pump is mounted at the upper end of the rotor. Of the positive type, it has 2 vanes sliding inside a liner mounted in the head, the capacity being considerably in excess of the requirements of the injection pump itself. Transfer pressure is at all times related to engine speed. An increase in speed produces an increase in transfer pressure, and similarly, a drop in speed results in the pressure falling. The pressure is controlled by a regulating valve, which bypasses fuel back to the suction side of the transfer pump. This valve also provides a means of bypassing the transfer pump when hand priming is necessary. Fuel entering the pump passes first through a gauze filter into the transfer pump, flows along a passage in the hydraulic head, around an annular groove surrounding the rotor, to the metering valve. This metering valve determines the exact amount of fuel entering the pumping element, and therefore the engine speed. Before explaining its operation, let's first see how the metering valve is controlled by governor action. The DPA pump is available with 2 alternative types of governor: the hydraulic, generally suitable for most automotive applications, and the mechanical, recommended where particularly close speed regulation is demanded. The hydraulic governor is of simple design, being operated by fuel at transfer pressure. From the annular groove surrounding the pump rotor, the fuel passes through the metering valve to an annular space round the valve. The operation of the metering valve can be followed more closely on this cutaway model. From the groove around the rotor, fuel at transfer pressure passes through the valve, which is hollow, then via transverse holes to the annular space. Endwise movement of the valve varies the area of the metering port registering with the annulus. In this position, the metering valve is fully open, and here, completely closed. As the valve opens, fuel passes through the metering port, thence to the inlet ports of the rotor. This drawing shows more constructional details of the hydraulic governor and metering valve. This actuating rack, the movement of which is effected by the manual or throttle control, is free to slide on the valve stem and is held between two springs acting in opposition. The main spring and the idling spring. The loading on the main spring varies according to the position of the manual control. As the control is operated to give increased speed, the valve is pushed towards the full open position by the governor spring. As the speed of the engine increases, transfer pressure also builds up, the increased pressure forcing the valve back against the mainspring until a balance is reached. When speed fluctuations occur, as the result of changes in engine loading, the governor provides an immediate and compensating change in fueling in order to maintain the selected speed. When the engine control is moved towards the idling position, the compression of the mainspring becomes progressively less, and the idling spring is compressed, enabling the reduced transfer pressure to operate the metering valve and perform the governing function throughout the idling range. A simple shut-off mechanism is also incorporated in the governor housing. A lever is provided for lifting the metering valve to the closed position, thus cutting off the fuel and stopping the engine. This is the DPA pump fitted with a mechanical governor. Although performing a similar function, the mechanical governor differs from the hydraulic type in both construction and principle of operation. In this version, the pump is somewhat longer, the housing being lengthened to accommodate the governor unit carried on the drive shaft. The main features of the pumping unit remain the same, with the exception of the metering valve, which in this instance is of the semi-rotary type. In this model, it'll be seen that the valve has a groove cut along one side, which registers with the metering port as the valve rotates. The rotation progressively controls the orifice to admit more or less fuel to the pumping element. Here, the valve is moving to the fully opened position. And now, completely closed. And once again, in end-on view. Valve closed, and now opened. The governor itself is of the flyweight type, the weight assembly rotating with the drive shaft. As the weights move inwards or outwards, under varying centrifugal force according to the pump speed, they operate a thrust sleeve which slides on the drive shaft. This endwise movement of the sleeve operates the control arm. This in turn actuates the metering valve. For simplicity, only the main parts are represented on this model. Movement of the throttle lever adjusts the load on the governor control spring, bringing about a change in the position of the control arm and hence of the metering valve, admitting more or less fuel to the pump as required. Tensioning of the governor spring provides increased resistance to the influence of the governor weights, so that with greater tension, resulting from increased throttle opening, governor control will be at higher RPM. For any setting, the governor will maintain the speed within close limits. Within the idling speed range, tension is removed from the main governor spring, and a light idling spring gives sensitive control at low revolutions. There's a simple shut-off device incorporated in the mechanical governor. As movement of the governor control lever is transmitted to the metering valve through the medium of a lightly loaded spring link, operation of the shut-off lever can therefore override the governor control, no matter in what position the weights may be, and turn the metering valve to the no fuel position. The design of the pump lends itself to the application of a simple automatic advance control mechanism. This hydraulically operated device provides a means of advancing the injection timing progressively as engine speed increases. The transfer pressure, rising with increase in speed, operates a servo piston against spring pressures, advancing the cam ring as required to give a predetermined timing curve. Here, in model form, we see the cam ring in the fully retarded position. As transfer pressure builds up with an increase in engine speed, the piston moves along the cylinder to rotate the cam ring to the fully advanced position. When the engine speed falls, transfer pressure decreases, and the piston and cam ring are moved towards the retarded position by spring pressure. The addition of automatic injection advance is of particular value in achieving optimum performance over a wide speed range, and can also assist cold starting. It'll be seen that the cam lobes do not follow a continuous lift and fall contour, but provide for a suitable retraction period at the termination of injection. This has the effect of unloading the fuel lines and prevents dribbling at the nozzles. Calibration and phasing, operations necessary in adjusting an inline pump, are unnecessary with the DPA pump, since they're provided for by the accurate spacing of the ports in the rotor and head during manufacture. The only adjustment provided on the DPA pump is that for maximum fuel setting. The maximum amount of fuel entering the pumping element is controlled by limiting the outward movement of the plungers. Adjusting plates located on the pumping section of the rotor enable the correct setting to be made. It'll be seen that the limiting slots in the plate, in which the projecting lugs of the roller shoes are inserted, and with them the plungers, is reduced or increased according to the setting. This large-scale model shows how this adjustment operates by controlling the maximum effective pumping stroke of the plungers. The correct setting is made when the pump is tested after manufacture and should not be altered without approval. The DPA pump is especially suited for high-speed operation. The rotating parts, being light, have little inertia. There are no return springs, the plungers being returned hydraulically. The driving torque is always in the one direction, and there's therefore little torsional oscillation to affect the drive. The pump is lubricated throughout by filtered fuel oil, the housing remaining completely filled during operation by back leakage of oil through a groove machined on the rotor. The present range of distributor-type pumps caters for engines of up to 2 liters capacity per cylinder. Already specified and installed in production engines operating around 4,000 RPM, even higher speeds are envisaged in the near future without any foreseeable difficulty. To sum up, the CAV Distributor-type fuel injection pump is by far the simplest and functionally the most satisfactory pump of this type yet devised. And its introduction, together with the pioneering work done by Perkins of Peterborough, has undoubtedly made an important contribution to the development of the modern diesel engine.